Hello, everybody. How are you doing?
Hello, Prof.
Hi. So what did you think about Friday's guest speaker?
Yeah, it was a good presentation. Oh, I joined in late because of some challenges. But I was trying to follow it online on those videos you posted.
Oh, good, good. Um, yeah, Shepard and I guess Desire's coming in now. For both of you two, I've asked Tamuka to reach out to you guys just to chat with you about going, about biotech in Zimbabwe, where you guys are going, what your plans are, and how we can, act as mentors and help you guys out in terms of your next steps.
Yeah,
Well,
even me, I really like the idea that there's someone from our side who can at least mentor us along this journey.
oh yes. And he probably knows a lot of, the cultural kinds of barriers that you guys have from where you're at, as well as the lay of the land there, as well as companies, all sorts of things. So he'll probably reach out to you guys sometime this week. So I'm looking forward to that. Um, let's see. So we're still on climate strategies, and we were talking about mitigation. We had started, I believe, into biofuels. Um, and that's where we're going to go ahead and pick up from. Let's see. Go ahead and share my screen, or at least a part of it. So this was in chapter 11. So you get a chance, go ahead and check out chapter 11. I think most of you have been following along really well with the book. In this section, we've been talking about what we can do about climate change, and there's three general categories that we've discussed: adaptation and mitigation, and we're also going to discuss geoengineering, fun stuff. Really important, we talked about this before, to know the difference between adaptation and mitigation. And Shepard, how would you define the difference between adaptation and mitigation in response to climate change?
Hello, Prof.
Yep.
Okay, I would define it in my simple term, the way I understand it. First of all, for adaptation, it's more like for is it adaptation? Yeah, for mitigation, we are trying to correct what have been already been done. Then for adaptation, we are working with what we have on the ground, something like that.
Yeah, both those are true. What's the key difference between the two? Desire, what's the key difference between adaptation and mitigation?
The key difference between adaptation and mitigation is, I think, so adaptation has to do with a way to cope after, like, let's say, an event has happened. Mitigation, we are trying to combat or to reduce the effects of that thing happening. For example, we can do mitigation by, let's say, in case of a cyclone, we try to, like, do the weather forecasting and try to evacuate people, like, to get them to safe environment. That's mitigation, because we're trying to reduce the effects of that thing destroying, or I mean, the flood. What am I saying? The the cyclone in this case. But for adaptation, we can adapt to climate change in ways that I'll take my point. Let someone go. I'm not sure.
Glory, you want to take a stab at it? What's the key difference between adaptation and mitigation?
Okay, the difference in adaptation is that we are trying to adjust to the climate change. Climate change is happening and there's nothing we can do about it. We are looking for ways of adjusting by bringing up strategies how to adapt to to live with the climate change. While mitigation has to do with the working to reduce the emission carbon, the CO2 that is being emitted. We need strategy like using the biofuel, how we can capture the emission. That is what mitigation looks at, how we can capture it and then leading to another use. That is the difference.
Yeah, so the key here is, at least for this context, mitigation is something that you're doing to eliminate greenhouse gases or reduce the amount of greenhouse gases that you're putting into the atmosphere. Everything else is adaptation. You want to clean up after a tsunami. You want to build seawalls to prevent more damage from sea level rise. Any of those things would just be adaptation. You want to engineer plants so they're drought tolerant. You're not changing the amount of greenhouse gases emitted. So it's not technically a mitigation of climate change. So they can be actions, they can be changes in behavior, new technologies, but for mitigations, think about, does it affect the amount of CO2 in the atmosphere, either now or in the future? And so those are the two things to think about. And so with mitigation, we looked at the IPAT rule because the IPAT relationship tells us about impact or emissions. And so we're trying to do things to change future emissions. We talked about how we can't really change population, or we don't want to reduce population. We don't want to reduce affluence. And since all these terms are multiplied together, if you reduce one, you reduce emissions. But really, population and affluence are not really targets that we want to look at. We can look at energy intensity and making things more efficient so they use energy better. But that we could never reduce down to zero. We could make it less. And so that would impact emissions. And so making more efficient batteries, more efficient light bulbs, those are all mitigation techniques because they're lowering our overall emissions of greenhouse gases later on. Carbon intensity is probably the biggest payoff where we can look at, because we can reduce carbon intensity to zero. Because remember, carbon intensity is the amount of CO2 per joule of energy. So if you look at your energy production, how much CO2 does it make? We talked about the largest carbon intensive technologies for producing energy: coal, oil, and natural gas. And then we talked about renewables. These are zero carbon intensity energy technologies. And there's renewables and non-renewables. We talked about all of these, I think. We talked about solar and wind. We talked about hydroelectric power. You can go back to the earlier lecture from last Wednesday on that. And then we started talking about use of biomass and the idea of growing biomass to give us plant carbon that we can then burn through combustion, which would indeed produce CO2, but we talked about it last time, how actually this can be a net zero carbon process, because for the amount of CO2 that you burn, you're going to have to regrow plants for the next cycle. And that's going to pull that CO2 back out of the atmosphere to grow the plants. Then you can do the cycle again. Now, this is a net zero carbon cycle. So using biomass is net zero carbon production. You do put CO2 back in the atmosphere, but you take an equivalent amount out. Now, the reason why it's a mitigation is if we switch from using fossil fuels to a net zero emissions energy technology, then we're reducing carbon emissions, right? We're still emitting carbon if we're using biomass, but we're taking that carbon out of the atmosphere. That's where we're getting it to burn. And if we switch from fossil fuels, which is taking it out of the rock reservoir, then we're in a much better position, because now we're leaving that carbon in the rock reservoir and we're only playing with the carbon that's already in the land biosphere reservoirs. And so we talked in general about what biofuels were. It's the idea that you grow a plant, and remember, plants, you know, they do photosynthesis to get energy. They use that energy to fix carbon. And the way that what they do with that carbon that they fix is they make sugars out of it. And those sugars, you know, can be various sugars in the plants that you eat, you know, like when you're eating fruits. But a majority of those go into making cellulose, which makes up the bulk of the plant, and lignocellulose, which will make up, you know, the bulk of, say, a tree, right? But you can take biomass that you grow, harvest it, and then pull out the sugars that you want, and then you can add like yeast, just like they do in beer making, to the sugars, and then the yeast will ferment it into an alcohol. And it could be bioethanol, it can be, we just stick the bio on it, meaning that it came from a biological source. So that's what bioethanol is. It's still ethanol, which is 2 carbons and an OH group on it. There's other options besides methanol. You can, or ethanol, you could make propanol, butanol. Butanol is something that you could actually directly put into a gas tank for a combustion engine in a car. And so we could go directly from this kind of production. You know, you grow your plants, you ferment the sugars, and then you create butanol that can go into a tank. The tank will do combustion, release that CO2 into the air, but you get energy from that, make your car go. And then you need to grow an equivalent number of plants for the next cycle. Anybody have any questions on this general idea?
So I wanted to ask, looking at the demand of energy when it comes to, like, coal delivers when it comes to energy. But I'm not sure how much or what it would take, or if biomass, like the way you explained, would really suffice to supply energy demand to meet the demand that coal is, or not only coal, but fossil fuels are delivering.
Okay, that's a great question. So a lot of our
like, how long would it take in terms of the span to try and?
Okay, so right now most of our energy production, electricity production, is done through coal, right? The burning of coal. We'd have to grow a lot of stuff to replace that. And I think rightly so, you're a little bit skeptical if we could grow enough to produce enough fuel for all of our energy. And I totally agree that that's a hard sell. I don't see us doing that completely, but it adds into the mix of the many things that we can do. So if we did wind and solar, for example, to try and replace coal and oil and natural gas, right, for electricity production, that makes up a big sliver. We use some of it with nuclear. That can make up a sliver. Remember, the problem with wind and solar was it's intermittent, so you need to be able to store energy. So you have these problems with batteries. Right now, one of the limiting factors on on the new types of cars that are hybrids or all electrical are these batteries. They're very expensive to produce. They're the most expensive part of the car, and they can only hold so much energy, and they use a lot of very um, a lot of materials and elements that are fairly rare and can be quite expensive, and also do a lot of damage to the environment in their extraction. So the idea here wouldn't necessarily use biomass to replace all energy production. Could still do wind and solar and gas, but it's part of the mix. So we have a large fleet of cars on the roads right now. Many of those are switching over to electrical, and that's great. But there's still several folks out there who don't want to switch to electrical because they don't like the charging stations and how long it takes. And so, there's these hybrid cars that do electrical or gas or a little bit of both. If we use biofuels for that, we could eliminate the burning of fossil fuels and use biofuels. That would bring down some of our emissions. But I agree with you. There's probably a limit to how much this could replace energy production. I don't know what that limit is. I haven't seen. It would be a. There's probably some papers out there that investigate that question. And if this was a route you'd want to go and say your project or future research or direction you want to take, we can look up those papers and investigate further. When we get to the protein engineering course, one of the examples of design we'll be looking at is a cellulase, which is something that's used in biofuel production. So we'll certainly have this conversation some more, but if you're interested in this topic, let me know and we can start the research early and continue on. Other questions about biofuels in general?
I was just thinking, I think this will really have to do with the human minds. We would like to make use of it, but there must be strategies to monitor how well are human beings planting the trees in order to make use of it. Looking at the process and the duration of the tree growth, the usage actually will be faster than.
Right.
Yeah.
So trying to use trees would probably be a big mistake. One, because of the growth, and the lignin in a tree, the wood in a tree, is fairly difficult to break down if you want to make a biofuel. Yes, you could burn the wood, but you'd probably be more efficient if it was easier to break down the sugars and ferment them, which is why one can look at algae. Algae can grow very fast. One of the fastest growing photosynthesizing organisms is Wolffia australiana, or known as duckweed. That's something that can be grown quite fast and possibly serve as one of those energy sources. Growing kelp is another one. Folks are creating kelp farms because they grow so fast. They can grow up to 18 inches in a day, so you can almost see them grow. And so some folks are already starting to invest in kelp farms that have these long ropes with the kelp attached that they harvest, and then they start putting them in their biofuel process for breaking them down. Bamboo also grows very fast, so that some researchers have already shown that bamboo can be converted to fuel. And so that's another interesting, promising direction. The world around us is supplying us with many of the answers that we need. We have to be able to listen to the world around us and tell us and listen to what nature is telling us. Nature has a lot of solutions. It's had problems with CO2 production in the past. But understand the difference between the different kinds of biofuels. So lignocellulosic biofuels, those are plants that have a woody part to them, usually things that we can't eat. If we use things like corn, we're going to drive up food prices because now you've got competition. When the farmer grows a bushel of corn, he can sell it to the people that want to eat corn or the people that want to use it for fuels in their car. And so it drives up the price because you've got more of a demand. And so we want to open up the pathways for breaking down the types of plant matter that we can't eat. And then it's a win-win for those farmers. It can be a part of the plant that they're not using to sell for food, which now they can sell for energy production. The science on this still has to be developed further. We have full biofuel processes that go from plant all the way to a usable fuel, but right now the technologies are fairly expensive. For example, the heat generated during the biofuel creation process is substantial. And so in these vessels, like if you've ever, mowed your lawn or put a big pile of glass clippings in a pile, if you reach your hand into it after a couple of days, you'll feel an incredible amount of heat as it's being broken down. A lot of heat is generated. And so in a lot of biofuel processes, if the heat gets too much, all of the enzymes denature, and so it stops. So they have to actually put them in these vats that are refrigerated to keep the temperature low enough so the enzymes can continue their biofuel creation process and break down the different components. Well, that refrigeration costs energy, and that drives up the price of the biofuel. And so right now, biofuels are not competitive at the pump. So if you go to the gas station, it would cost more to buy a gallon of biofuel than it would gasoline fuel, which means consumers will always pick the cheaper thing. And so it's really not a competitive solution. But all we need to do is improve the technology. So one of the projects they're working on in my lab is to try and design a cellulase that will break down cellulose in one of these biofuel processes that's thermostable. So you don't have to refrigerate it. It can work at the high temperatures and break these things down. It makes the process of making the biofuel cheaper, which means more people can access it. So in general, you've got these, remember your plants either make cellulose, hemicellulose, or lignin. Primary difference between cellulose and starch, which is what we can eat, is just this connection here. So these are glucose molecules chained together, but in the case of starch, you have a connection. You see how this goes down as opposed to this going up. This is called an alpha linkage when it goes down. And when it goes up, that's a beta linkage. That's the difference between, so starch, you see this kind of linkage in fruits. You can break this down, but the beta linkage, you can't. Animals have no enzymes that break up this beta 1,4 linkage. And the 1 and the 4 come from how we do numbering on sugars. We number the carbons kind of clockwise, starting after the oxygen. So 1, 2, 3, 4, 5. Here's our 6 carbon sugar. The bond in starch and in cellulose is between the 1 carbon of one sugar and the 4 carbon of another sugar. So it's a 1,4 linkage, and it's either down, which is alpha, or up, which is beta. And animals can't break that down. But we have many enzymes that can break it down. We can harvest those enzymes and use that in our biofuel process. And so lots of different possible sources for biofuels. they'll generally go through the same kind of process of cleaving up the polysaccharide, hydrolyzing it, fermenting it, and creating a biofuel. So it's net carbon neutral, it's renewable, it can be used in existing car engines for combustion. In other words, we don't have to adapt old cars to be able to use that kind of stuff. And it's less dependent on battery or electrical technology. So would a biofuel be a case of adaptation or mitigation?
Adaptation.
I hear
It's
one vote for
mitigation.
adaptation.
As mitigation, Prof.
Mitigation. Explain
Yes.
why, Gloria. You are correct.
Adaptation.
Gloria is correct. It is a mitigation. Why is it a mitigation,
Yes.
Gloria?
Because we are harvesting the carbon, the CO2. We are harvesting it from using the fuel that is more reliable, more renewable, that is not creating harm in the environment.
Right. Remember, our definition of a mitigation is it has to reduce the amount of CO2 in the atmosphere. Now, I've just said that the biofuel process is net zero. It doesn't increase or it reduces it. So where is the mitigation? It's still a mitigation. Where does the mitigation come from? Brenda, do you have any thoughts on this?
I think the mitigation comes in because we are not increasing the carbon dioxide in the atmosphere. So if we continue to use this process of harvesting biofuels, it will be a mitigating process as it is not increasing any amount of carbon dioxide into the atmosphere.
Right. So it's the switch from fossil fuels to biofuels that's mitigating, because fossil fuels were emitting a lot. And so if we switch from something that emits a lot to something that's carbon neutral, that sucks up as much as it emits, then there's a net lowering of our emissions. So our emissions decrease from what they are now, because right now we're just taking stuff out of the rocks and putting it into the air. Here, we're taking stuff out of the air just to put it back into the air. And so it's net neutral. So the mitigation comes from switching from fossil fuels to biofuels. You know, however much we're going to do of that. Biofuels might not make up all of how we get rid of fossil fuels, but say we're going to replace 25% of fossil fuel energy generation with biofuels. Once we do that, we got this mitigation. We've now cut our emissions down. After that, biofuels will just be neutral. It will no longer be mitigating because we've already done the conversion. So the point here is, earlier in the last lecture, we talked about how biotechnology is often a form of adaptation. It can also be a form of mitigation, right? And so that's shown by biofuels and these trees that grow faster that we talked about. There's also something called biosequestration, which is biological processes which take carbon dioxide out of the atmosphere and then create plastics or other things where the carbon is now sequestered, where it's not going to get burned, it's not going to be done, nothing's going to be done to it, and it's going to stay in out of atmospheric form. And so these are lots of different avenues in biotechnology, and they have their own related fuels. So biofuels is a whole field of biotechnology, which is very lucrative. And almost all of these involve the techniques and fields of directed evolution and protein design. And we'll talk about those when we talk more about in our protein class, when we talk about protein structure, function, and design. Any more questions about mitigation? Okay, cool. I'm going to switch over now to talk about the next fun area, which is geoengineering. Okay, this is also in chapter 11. So we've covered adaptation, we've covered mitigation, and the third area is this idea of geoengineering. What does that word make you think of when we say geoengineering?
Engineering the land.
Yeah,
Some
engineering
capacity.
engineering the planet, right? And so one of the techniques that's discussed quite a bit is something called solar radiation management, or SRM. And then the other one, the other big category is carbon dioxide removal. So both of these types of geoengineering are trying to get at fighting climate change. Okay, there's other kinds of geoengineering which don't have anything to do with climate change. We're not going to discuss those. We're just going to focus on climate change. And so for solar radiation management, let's tackle that one first. Let's go back to our favorite equation. Okay, this one. We know that the surface temperature is going to be related by this equation, where N is the number of layers in an atmosphere, S is our solar constant, A is, or alpha is our albedo, and then this is just the a constant down here, right? That's the Stefan Boltzmann constant. So really our only variables are the number of layers, the solar constant, and the albedo. The solar constant is pretty much fixed based on our location in space, right? So the other two is lowering N, and we can affect that by lowering the greenhouse gases, or changing the albedo. What's the effect if we increase the Earth's albedo? What happens then? If we increase it or we lower it? What's going to happen to temperature?
The temperature would decrease with the increase of the albedo.
Right, right. So say let's just look at a one-layer planet. Say we had a solar constant of about 2,000 watts per meter squared, in albedo about 0.4. We just stick those into our equation. Here's our solar constant, here's our albedo, and that would give us a final temperature of 321 Kelvin. Okay, now assume for a moment that we could, or that the society living on this one-layer planet increases their greenhouse gases. Okay, so the greenhouse gases go up, and so instead of N being equal to 1, we're gonna N increases to 1.1. Okay, that's going to give us a new temperature of 3.25. If you put those numbers in here, you're going to get a new temperature of about 3.25. Okay, I have that reversed there. So now, if in response they say, okay, well, we've increased the temperature of the planet because we've made more greenhouse gases, but what if we can increase the albedo? And so if they increase the albedo from 0.4 to 0.425, that will then bring down the temperature back to the original temperature of 321. So there's a way to mitigate, well, I shouldn't say mitigate, there's a way to bring the temperature back down just by changing the albedo, okay? And so trying to increase the Earth's albedo is called solar radiation management geoengineering. You're reducing energy in, right? And the most common idea, a large-scale strategy, is the idea of releasing sulfur into the stratosphere, because when you release sulfur, it forms little aerosols. They're tiny little droplets, and they have a negligible fall speed, so they just stay up there. And they reflect sunlight back into space because they're reflective, and that stops a lot of the energy from coming back in. And the physics on this is pretty sound. A lot of people made a lot of calculations on this, and so there's a high confidence that it could actually stabilize temperature. Now, there's a lot of different ways to do solar radiation management. You can some people propose putting little shades floating out in space to reflect sunlight. The stratospheric aerosols, which is the idea of releasing sulfur into the stratosphere. There are chemicals you can use to whiten clouds, and people have even thought, well, why don't we just whiten the rooftops of our buildings? All of those would have an effect to increase our albedo. But this idea of putting sulfur into the stratosphere has been well researched. There's sulfate particles that we know we can make in large quantities. If we put them into the stratosphere, we know they make these aerosols. And we know that this effect works because it's one of the things that volcanoes do. So when volcanoes spew out into the atmosphere, often they spew a lot of sulfur compounds into the atmosphere, and that tends to reflect a lot of the sunlight back. And so we see this cooling effect. It's fairly well documented. Okay. So what do you guys think about this idea of injecting sulfur into the atmosphere to make these aerosols to increase our albedo?
I would question the compounds in particular if they don't cause any reactions within the atmosphere leading to, in the case of rain, we might have like sulfuric acid, like acids that might come from the reaction of water in the atmosphere, and that would also cause another problem. So I'm not sure if that would be the case.
Yeah, I was also. Well,
go ahead, Keldrin.
I was also wary on the on a possible snowball effect of course adding the sulfur into the atmosphere, which will probably research is kind of insinuating that this is somewhat of a good idea, but I think there's always drawbacks from which we learned in this class of, okay, we have a solution to this, but now we're causing this issue.
Right.
Playing off of what Desire has said.
So here's something that we could actually do today. There's no new technology we need to develop. We could send planes up there. We know how to make these sulfur compounds. Actually, they're generated a lot by a lot of our industries already. We can do it at that large enough scale to actually be able to do this today or tomorrow. And then we know from the physics, from our favorite equation, that it would lower the surface temperature pretty quickly. So let's walk through a little bit about what some of the drawbacks might be. Okay. So first off, is SRM, is it removing any of the CO2 from the atmosphere? No. So would it have any effects on things like ocean acidification? Right? It wouldn't change that. It wouldn't change ocean acidification at all, because it's not changing the amount of carbon dioxide in the atmosphere. So the amount of carbon dioxide in the atmosphere that dissolves in the ocean will still be the same, right? And it's not addressing, it may, in a way, give us permission to continue to put more CO2 into the atmosphere, right? Because we're not getting any negative effects. And so we keep putting more CO2 in the atmosphere, which means we'll have to continually put more sulfur in our atmosphere to keep up, right? Okay. One of the predicted possibilities from this is exactly what you guys said, is it could lead to new problems. So one of the predicted things that could have a big effect on are changes in precipitation. We don't know how precipitation will change, but when Mount Pinatubo blew up a few years ago, that led to droughts and changes in precipitations over large swaths of land. It moved the precipitation patterns. So we could be talking about a whole new set of problems, just like you're talking about. There's also issues of governance. Like I said, we could do this today, but who's going to do it and how much, right? So one country is just going to decide to start changing our atmosphere. Do all the countries have to agree, you know, and come to a consensus of how much sulfur to put in the atmosphere and when? And what if just one country is affected by these droughts, but the other countries aren't? You know, is that a step towards war if some countries are being adversely, you know, impacted by what these other countries are trying to do to save themselves or to save all of this? And then the last problem with SRM, if we were to think about it and consider it as a strategy, and we might have to, we might get to the point, because of a lot of our predictions right now, we're well on our way to more than 3 degrees of warming. And so if we don't get our act together in a decade or two or a few decades, this might be our only option to bring us back from the brink. Because remember, we cannot let the permafrost melt. If the permafrost melts, it's catastrophic, because we'll put way more CO2 into the atmosphere than humans ever have before. So this might be something that we're forced to consider in the future. And so it's important to talk about what you have to be careful of. So here's a plot showing a planet that's warming fairly quickly. Here's temperature over here, the temperature anomaly, and here's the years. And it's going along, we see it going on. Now, say we decide to use geoengineering and start adding sulfur into the atmosphere, and we're adding enough as we go along to offset the temperature change due to these greenhouse gases. Okay, so our temperature doesn't change. Our greenhouse gases are still going up, but the temperature anomaly is staying stagnant. Okay, so at some point, the countries decide, okay, we're going to stop adding sulfur to the atmosphere. So say we stop adding sulfur in year 50. Okay, what do you think is going to happen to the temperature anomaly?
I would have. Well, the temperature anomaly would increase.
Temperature would start increasing. So how long does it take for sulfur to leave the stratosphere? We've actually already talked about this a little bit a while back when we were talking about volcanoes. How long does it take a volcano, when it has an eruption that puts sulfur into the atmosphere, how long does it take for that to leave the stratosphere? It's usually just a few years.
Isn't it a few days?
No, it's a few years, about 4 years. About 4 years. So on our time scale, not very much at all if we've got decades on here. So within 4 years, that albedo is going to go back to what it was. And so what we'd start seeing is a rapid rise in temperature, right? It would start shooting up because now we're have to take into account all this new CO2. And so we'd see a much more rapid rise than we did had we not added the sulfur into the atmosphere. And that's probably worse than if we just let it gradually go up, because the faster things change, the harder it is for us to adapt to them, and for like animals and other species to adapt for them. So if we do have to use an SRM, we really have to have a plan on how we're going to wean ourselves off of it, how we're going to end it. And we have to stay committed to continuing to inject sulfur until we've got a plan to wean ourselves off of it and deal with the problem. So we'd have to bring our greenhouse gas levels down before we stopped adding the sulfur into the atmosphere. Okay. So the last one we have to talk about, we'll talk about this on Wednesday some more, is carbon dioxide removal. This is the direct removal of carbon dioxide from the atmosphere, and then sequestering it. And I'll try and send you, there was a great New York Times article that was out 2 days ago about a company that's doing this direct capture, and we'll talk about the technology and stuff. But the idea behind that is, let's directly take the CO2 out of the atmosphere and get rid of the problem. Wouldn't that be nice? Okay, that's about it for today on the geoengineering. We'll talk a little bit about carbon capture next time, and then we'll start getting into actually some of the politics and some of, what are the Paris Accords, what are some of the actual climate strategies out there that countries have come up with that are pathways to not total self-destruction. Has anybody heard the news in Iceland? You should probably check the news. Look up Iceland, what's going on. They got some serious volcanic activity going on there. Iceland is the home of what was once a super volcano, which it actually had a huge climate impact when it had a massive eruption, I think 2,000 years ago. But they're seeing lots of pretty extreme volcanic activity there, which, potential source of more CO2 going in the atmosphere, but also some cool weather due to albedo changes. So check it out if you can. And I will talk to you on Wednesday. Bye, everybody. Thanks a lot.
Thank you, Prof.